time. And so now what I will do is, let me come back to tensors. And once I get to, you see, so as you saw, the Maxwell's equations involved derivatives of the energy moment, the electromagnetic field tensor. Like, for example, we had Fik, comma k equal to Ji, and F and epsilon I J K L KL, comma J is equal to 0. You remember, these are the two Maxwell's equations. Last time we did it, right? Not last time, maybe last time, I think.
Yes.
Okay, so these are the Maxwell's equations. And okay, just to, so let me just give it here. Yeah. So the thing is, so here we defined an AI as phi A vector. The covariant will be phi minus A, because eta, alpha, beta will have minus sign in the spatial sections. Now I do a gauge transformation as AI going to AI prime is given as Gij A prime. Gij. What? See, remember that this A to A prime is not coordinate transformation. It is gauge transformation. So there is nothing like Gij prime. You understand?
Yeah.
Do you get it?
Yes.
See, this is a gauge transformation, not a coordinate transformation. So Gij remains Gij. So Gij A prime J, which is equal to Gij Aj minus, this thing. Okay, and this is equal to this. Okay, so this is the gauge transformation. And electromagnetic field tensor is given by this Fij. And then when you, okay, so now if you do a gauge transformation in Aij, make an F prime Ij, and you substitute this, you will find that there is a term del xj by del xif and del xi del xjf with opposite sign. And since in partial derivative, the order of derivative does not matter, these two will cancel out. So it will come out as this, which means Fij is a gauge invariant object. Okay? You get this?
Yes.
Yeah.
Now, if Fij is a gauge invariant object, the components of Fij should be physically measurable. See, you see, gauge, something which depends on gauge, you should not be able to measure it. Right? Like vector potential. But what you can measure is electric field and magnetic field, because they are gauge invariant. And you find that this Fik components are basically the consisting of electric and magnetic field components. And we defined a current density, 4 current density, which is basically phi, comma, the 3 current density. This is called the 4 current density. And having defined all this, this was the Maxwell's equation. And this set of Maxwell's equations, when you split it into time and space, will come out to be this one and this one. And the other set of Maxwell's equation, this thing, will come out to be the divergence of B is 0 and the curl of E is minus del B by del T. And this can be written in this form, in which you have KLM JKL, that is, I cyclically rotate it, and that is equal to 0. I also mentioned that this quantity Fij is an invariant, as you can see, it's a scalar, and it is proportional to E square minus B square. And another quantity F tilde Ij, Fij, which is a dual. So it's epsilon IJKL, FKL Fij is E dot B. And this is an invariant under Lorentz transformation and rotation, but not under inversion. This is okay. So as long as you are not doing an inversion, this is also an invariant. Okay.
Yes.
Can you proceed? Okay.
Yeah.
Right. So this is where we were. Now, we also started tensor calculus, and that is where I will now take the lead. Now, the point is, you had these Maxwell's equations where we had partial derivatives of the electromagnetic field tensor. We also saw, if you remember, which I will also recapitulate, that the partial derivative of a vector is in general not a vector, or it's not a tensor. Right?
Yes.
You remember we showed that.
Yeah.
Okay. Which means a partial derivative of a tensor is not likely to be a tensor in general. But Maxwell's equations involve partial derivatives of tensors. Now we saw that if a mathematical equation should represent a physical reality, then the equation should involve tensors on both sides of the equation. You remember this? Because once you have a tensor equal to tensor, when I do a coordinate transformation, both sides will transform in the same way, and hence the equality will still be maintained. And that is what you require. You don't want that the physical reality should change just because coordinates have changed. Is that okay?
Yes.
Okay. Which means, since this does not behave like a tensor under general coordinate transformation, we need to make a new formulation of Maxwell's equation, which will be valid even in curved spacetime, for which flat spacetime will be a special case. And not only Maxwell's equation, any physically relevant equation which involves differentiation will have to be generalized to take care of the fact that partial derivative is not a tensor. Okay. And this leads us to this whole subject of tensor calculus. So as I said, mathematical formulation involves differential equations. Hence, in addition to tensor algebra, tensor calculus is also needed. Now, transformation properties of derivatives of scalar, as we saw, this phi xi equal to phi bar xi bar, right? There are two different coordinates. So here I have xi going to xi bar. Now I take a derivative of the right hand side. Del by del x bar I phi bar x bar is equal to del by del xj del by del x bar I del phi bar by x, del phi bar x bar by del xj. Just the usual law of partial derivative. Okay. But now I know that phi bar x bar is phi x, so I can write it this way. Suppose I write this quantity as a covariant vector, as a single lower index object phi bar I by b bar I. Then this quantity becomes a single lower index bj. And this quantity is this. This immediately implies that actually bi is transforming as a tensor, as a vector. Right?
Yes.
Okay. But this is no surprise, because if you remember, we defined the covariant vector as those quantities which transform as partial derivatives, right, of a scalar.
Yeah.
Originally, when we introduced covariant derivative, we introduced covariant vectors, we said those single index objects which transform as this quantity are called covariant vectors. So naturally, by definition, this is a covariant vector. Okay.
Yes. Yes.
Yes.
So first of all, so we see that partial derivative of a scalar is a covariant vector. Now let us see partial derivative of a tensor. And this is what we had done last time. So I will just do it again. So I'll take del ai by del xj. Now, if I substitute for a here, actually I've done this. I mean, do I need to do this again? Do you remember?
We remember this.
Okay. So we see that this quantity would have transformed as a tensor, but for this term, which plays a spoil sport. It is the addition of this term which spoils the tensor nature of partial derivative of a vector. Now here it requires a bit of an interesting point which you need to remember, which is, now the first term in the LHS spoils the tensor nature, but if xi to xi bar was a linear transformation, then the partial derivative of xi with respect to x bar will be a constant. And hence the second derivative will be 0. And so this term will become 0. So for the case where the transformation is a linear transformation, like Lorentz transformation or a rotation, this problem of partial derivative not being a tensor does not arise because they are linear transformations. That is why when you did special relativity, you never had to bother about the fact that partial derivative is not a tensor. Is this important and subtle point clear?
Yes.
You know, it's a very important point. It's a point. So that is why, as long as it's special relativity, you don't bother about it. But the problem will come the moment I go to even a simple thing like from Cartesian to polar, because polar coordinates are related to Cartesian coordinates by nonlinear transformation. Okay? And that is why, for example, del by del r or del by del phi is not a vector. Okay? So now let us see how to deal with this situation. So let us start with the case of vectors. And so let me just copy this here. Yep. Now, as I was telling last time, why does this happen? As I was saying, now let us take the case of particle moving with uniform velocity v in the x direction. Okay. And so I have this thing. This is my observer. This is my x direction. This is my y direction. And a particle is moving here. Now, at a certain time, it is here, and at a later time, it is here. Now, what is the velocity vector in Cartesian system? At t equal to t1, it is v equal to v0. At t equal to t2 also, it is v equal to v0 because it is a constant uniform velocity in the same direction. However, if I take polar, then at t equal to t1, this v vector bar will be equal to radial velocity 0, the theta direction is v. But at t equal to t2, if you look at it, this direction is Vr and this direction is V theta. You will have V, this is equal to some Vr V theta. This you remember I mentioned last time.
Yeah.
Okay. So what is it that you are seeing? You're seeing something funny happening. You know that the velocity of the particle is not changing. There are no forces acting on it. Yet the component of velocity is changing in the polar coordinate, which means that the change in this component of velocity is basically a coordinate artifact. It happens because while Cartesian coordinate maintains its orientation, the polar coordinate here was, this was r and this was theta. Here this was r and this is theta. So the coordinate then itself is rotating. And that is why there is this artifact that the velocity component in this coordinate system seems to be picking up value as it moves, although physically there is no change in the velocity. The moral of the story is, okay, so now if suppose a particle is indeed moving with a non-uniform velocity, then just by measuring the components in polar coordinates, I cannot say that this is the physical change in velocity, because the total change in velocity in polar coordinates will be 1 because of its physical change plus the artifact because of the coordinates rotating. So our aim is to construct a mechanism in which the change from the change in a vector, I should be able to extract away the coordinate artifact so that the rest which I have is my physical change in the vector. Is this plan clear?
Yes.
Okay. What about others? Yajil?
Yes, yes, clear.
Anil? Yeah, what has happened to others? Hey, Anil, you're saying something?
No, sir.
Okay. What has happened to others? I don't know. Oh, okay.
I think Snigdha will be there in the that thing going on celebration.
Oh, you came away from that, huh? Okay.
Yeah.
Okay. So now we need to construct a way of extracting this out. So in fact, this is precisely why the derivative of this quantity, I mean, the partial derivative of AI is not a tensor. It is because the partial derivative of AI contains not only the physical change of AI, but also the coordinate dependence. So these two are intricately related. And so I can say that DIAI is equal to del AI by del XJ dxj. Okay. This is a contravariant vector. What about this?
Covariant.
No, it is not a tensor. Because just now we saw that partial derivative is not a tensor in general.
Yeah.
And hence, DAI is not a vector. And it is not a vector because it has both the physical change as well as the coordinate dependence hiding in it. And now, next program is to construct a mechanism of extracting out the coordinate dependence from this. Okay, am I clear?
Yes.
Okay. So now let us do that. Okay. So now let me say the following. I will call that I will say that the physical change in AI, let me call it as DAI, as against small d. I will say that this is the physical change. This has something in which the coordinate dependence has been extracted out. And so I write that D AI is equal to DAI minus delta AI, which is purely a coordinate artifact. And next thing which you need to do is to construct what is the form of delta AI so as I can take it out. So let us consider what is AI. So what I do is I move an infinitesimally small distance and I calculate what is delta AI when moving it. Now here you need to, okay, we'll come to that. First of all, when you are doing an infinitesimal change, what are the things in which A will depend on? First of all, it depends on the amount of movement, delta X. But it doesn't have to be delta Xi. It can be the most general combination of X. So I will call it delta Xj. It is proportional to delta Xj. Further, it is also dependent on the A itself. Larger the magnitude, larger the change. Are you with me?
Delta is what?
Okay, so it is an infinitesimal change in the position.
Okay.
Okay. It should depend on this. It should also depend on A, K. Now,
I don't quite get this AK. Like, why does it depend on AK?
okay. So look at it this way, that if suppose I have, okay, so if I have, if I have a vector which is twice AK, twice AI, when I make this transformation, the change will also be twice.
But, yeah, but that means the magnitude is what matters. No?
Yeah,
I
yeah,
mean,
for each component. No? It's not a vector, it's a component I have written, AK.
okay, got it.
Okay. And so it depends on these two. And remember that I am not saying it's depending on Xi because it can depend on any code, because the most general linear connection is a matrix connection. So like if suppose you have a vector A and a vector B, what is the most general linear connection between them? It is AI equal to some C ij bj. It doesn't have to be AI equal to constant times bj. The most general linear thing will be a matrix multiplying it. Okay?
Yes.
Okay. And so the constant of proportionality I will call here minus gamma I k j. Now you can ask, why have I called minus? Since I have not defined gamma, I can always define as minus. If a person doesn't want to put minus, that gamma will be minus of this gamma. That's all. So I'm following one convention where this is what the coordinate dependent change is. All right.
Yeah.
And so here I have defined gamma, right? No, I have not defined gamma. I'll come to gamma now. Okay. So this is some quantity called gamma. And so the physical change DIAI will be equal to DAI plus, I'm extracting it out. This minus and this minus will become plus gamma ij, sorry. Okay. And now I can say that this is D, okay. So I can now, what I can write is this quantity is what? It is del AI by del xj dxj plus gamma I kj ak dxj, which is equal to del AI by del xj plus gamma ikj ak times dxj. Okay, which means, so dAI is this. When I say dAI is equal to del AI by del xj dxj, I call this the partial derivative of A with respect to X. When I have this physical change, I call this the covariant derivative of A with respect to J. And this, so physically what is happening is, this quantity is the one. Suppose I have a particle moving with no force acting on it. Then you expect that dV by dt should be 0, right?
Yes.
Okay. As we saw in polar coordinates, that is not the case because the coordinates are changing.
Yeah.
However, if I derive the form of gamma, which I will do, and put it here, this quantity will make sure that this dAI, that is dVi, will remain 0, whether you use polar or you use Cartesian coordinate. That is, it measures the physical change in the velocity and not something which includes the coordinate artifact. Okay.
Yeah.
Is that all right?
Yes.
Okay. So in our usual notation, I will write dAI is equal to AI comma j plus gamma I jk ak times okay, this is kj. It will not matter, which I will tell you prove later, but right now I'll just maintain this order. Aj. And so I call this dAI as AI semicolon j dxj. And so the covariant derivative, that is AI semicolon j, is equal to AI comma j, which is partial derivative, plus gamma I kg. AK. Does it remind you of something? Oh, probably not. You people must not have done non-abelian gauge theory or something, right?
No, yes.
So there is something called the non-abelian gauge theory, which is called Yang-Mills theory. And this has a lot of similarity with that. Okay, well, I mean, because that is the theory which describes quarks in nucleons and so on. Okay, so, okay, well, let's forget this. So this is called, and this is called, either it's called connection coefficients, or as usual, I'm not sure about the spelling, Christoffel symbols. Okay. So there exists such an object. I have not yet told you how to get it. Right?
Fish, in this equation, how do you differentiate the covariant derivative and the ordinary derivative? Both
I am
look the
sorry,
same.
I'm sorry, I'm sorry.
Ah,
Yeah, it's a semicolon. So semicolon is for covariant derivative and comma is for partial derivative. Okay. Now, Since my covariant derivative is a physical change, I demand that this should be a tensor. Otherwise, there's no reason for doing all these things. In other words, I choose my gamma ikj in such a way that ai semicolon j is a tensor. Is that all right?
Yeah.
Okay.
Yeah.
So using this and the fact that ai comma j does not transform as a tensor, we can next get the transformation properties of gamma. So I have a bar a semicolon b is equal to del x bar a del x I del x j del x bar b a I semicolon j. Are you with me? Because you look at a bar a semicolon b as some tensor t bar ab and a I semicolon j as some tensor tij. Is okay?
Yeah.
Okay. Now, I will write it in terms of partial derivatives on both the sides. Okay. So this will be a bar a comma b plus gamma bar, that is gamma in the barred coordinate system, a j b c a bar c. Is it okay?
Sesh, gamma does not transform like a tensor, but
It
gamma
won't
times,
transform like a tensor, but I said just said it transforms. That's all.
but gamma times A does it transform like a tensor? Because I
No,
mean,
it doesn't.
oh, so uh,
That's what I will get it.
okay.
See, what will happen is partial derivative of A does not transform like a tensor.
Uh,
Gamma does not transform like a tensor. But
Gamma
they
times
will
A.
deviate from the tensor transformation in such a way that in this combination, both will cancel out.
Oh, okay.
So that is the whole, that is how I choose gamma.
Okay.
Okay. And this is equal to del x bar A by del x I del x j by del x bar B a I comma j plus gamma I j k a k. All right. I'll just substitute it there. Okay. But now, okay, so this I will write as del x bar a by del x I del x j by del x bar b a I comma j, which is a tensor kind of a thing, plus del x bar a by del x I del x j by del x bar b gamma I k j a k. All right.
Yeah.
Okay.
Yeah.
And this is equal to on this side a bar a comma b plus gamma bar a c b a c. Now I write a bar in terms of a because I know how partial derivative transforms. It doesn't transform as a tensor, but I know how it transforms. I already derived it, right? Here.
Yes.
Okay. And so here, this will be,
Say here you've written gamma bar times A, but above you've written gamma bar times A bar C.
pardon?
Here, I mean, in the last before equation, you've written gamma bar times AC, right? But in the above one, you've written gamma bar times A bar. Which one is it?
Oh, I'm sorry. You're absolutely right. You're absolutely, I'm just copied that side, that's all.
So if this A bar becomes A, shouldn't we have a transformation for that too?
No, now I'm going to write it.
Okay.
Okay. So now I'm going to first of all write the transformation. So see here, I will just interchange bar and unbar. That's what I need to do here, right? I want to yeah. So here, for example, I will just rename these. Okay, I will just write it again. That's better.
No, Sesh, what I'm asking is in the previous equation, there is A bar on the left-hand side, but on the right-hand side, you've converted it to A without, I mean, including the coordinate transformation.
No. I have just opened the bracket here. That's all. This into this and this into this.
Shouldn't it be A bar power K?
Which one?
The next to the Christoffel symbol, the right-hand side.
Here.
Ah,
No, it is
shouldn't
AK, no?
But
Because
on
here I have got the unbarred.
Okay.
Okay, so I'm not doing a transformation. I'm just opening the bracket and multiplying.
Okay.
Okay, and so now, okay, so I will write this as, let me just write this. A bar A by del X B.
They can just put this on the right hand side and compare it. No, like why to change it to bar again?
I will, okay. The problem will be, I will tell you. Then I'm allowed to invert this partial derivative, which is a pain.
Okay.
Okay. So, I mean, because del x bar A by del x I is not del x I by del x bar A. I'll have to use whole transformation then.
Okay. Then better to convert it. No.
Okay. Yeah. So it is del x bar, this one del x bar A is equal to del x I by del x bar B del 2xa by del xi del x bar A, then del xi del xk a k plus del x bar A by del xk del x I by del x bar B del A k by del xi. Is that okay? I have just made bar to unbar, A to B, and J to and A. So I to A and J to B. So I have made, bar, unbar. Just 1 minute. Just hold on. I'm just getting a phone call. Yeah. Okay. So I and J and A interchanged, J and B interchanged. That is all I have done. And K remains K because it's a dummy index. Are you with me?
Yes.
Yes.
Okay. And now I'll substitute this over here. So I will have del x bar A by del x I, sorry, del x bar. No, what am I writing? No, I have to substitute this thing here, sorry. So I have to put this here. So I will have del xi by del x bar b del 2 x bar a by del xi by del xk. Okay. AK. This is the first term plus the second term del x bar A by del xk del xi by del x bar B del AK by del xi. It's completely wrong. No, that's all right. Yeah, it's okay. Yeah, that's okay. Okay. And this is equal to the right-hand side. Okay. Now, what you notice is that this quantity and this quantity are the same. Why? Because here J and I both are dummy indices. So I can replace I by K. And I will now replace J by I. They are dummy indices. And now these two terms are exactly equal. Are you with me?
Yes.
And these two will cancel. Okay. Further, I have the second term here, which I have not yet written. This is plus gamma bar A CB del x bar C by del x K AK. Is it okay? This
Yeah.
quantity. Okay. Now what you see is that you have the AK. Now this thing is true for any AK. Any vector AK, this is true. So I can equate the coefficients. Are you with me?
Yeah.
Okay. So I have del xi by del x bar b del 2x bar a by del xi del xk AK plus gamma bar A C B del x bar C by del x K AK is equal to gamma is equal to del x bar A by del x J del x J by del x bar b gamma, yeah, this is I, not J. Gamma I kj ak. So first of all, we say that this ak can be got rid of. So I have, I mean, you know, you have to be careful with the argument. It is not that you are cancelling ak. See, because ak is not a number, it's a sum of a1, a2, a3, everything. It is true because any arbitrary ak, it will be 0. So you can remove it. Is that okay?
Yes.
Yes.
Okay, fine. So now you have this. And now I will, okay. So now I will write it as gamma bar A CB del x bar C by del xk is equal to del x bar A by del xi del xj by del x bar B gamma ikj minus del xi by del x bar B del 2 x bar A by del xi del xk. And now what I do is I multiply both sides by del x k by del x bar d, suppose. Okay. All right.
Yeah.
Then what will happen is this will become gamma bar ACB del xk by del x bar d del x bar c by del xk, and this is equal to gamma bar ACB delta function of CD. Okay.
Yeah.
And this
Yeah.
is equal to gamma bar ADB. If I multiply the same thing here, this will become del xk by del x bar d del x bar a by del xi del xj by del x bar b gamma ij ikj. Now remember, I have not completed. This is like a tensor transformation, with I being contravariant and other being covariant. Just a minute. கொஞ்ச நேரம் கழிச்சு பண்ணலாமா? Okay. So this transforms like a tensor, but then that is not the whole story. There is an extra bit. Okay. And what is that extra bit? That extra bit comes from here. It is minus del xk by del x bar d, which we multiplied here, times del xi by del x bar b, del 2 x bar a by del xi del xk times gamma ikj. I am not happy with this. No, no, no. What am I doing? Hey, there is. Sorry, sorry. Array, sorry. See, this is the equation we got, right? And then we multiplied this quantity on both sides.
Yes.
Right? So from here we got this thing.
Yes.
Okay. Then, so I need to just do this one here. So it will be del xk by del x bar d, del xi by del x bar b, del 2x bar a by del xi del xk. So I get the transformation properties of gamma as gamma bar a db is equal to del xk by del x bar d, del x bar a by del xi, del xj by del x bar b, gamma ikj, which is a tensor-like part, but then there is an extra non-tensor part, which is and this is exactly what was spoiling the tensor nature of A. Okay, that is this portion, which has a first derivative, first and second derivative. Are you with me?
Yes.
So you have constructed gamma in such a way that the new quantity, which is the covariant derivative of A, transforms as a tensor. And so this is the physical quantity. I have not yet derived the form of gamma. I will come to it because I need to do several steps before I do that. But I know that there exists a quantity called gamma. I know its transformation properties such that this combination makes it a covariant derivative. Okay. And so.
But I'm just worried about the order of the indices on gamma, like A, B, C, where should we position it?
Pardon?
Like A, D, B, right, on the gamma tensor.
Huh?
Like, is this the right positioning or like does it change? Like, I'm confused about the index position.
No, that's K up, down.
Okay.
A comes here, D here, B here, J, and I. So if you forget this, gamma will behave as if it's a tensor. If you forget this portion.
That's okay.
Exactly the way in the partial derivative of A. There's one portion which was transforming like a tensor, the other portion was not. And these two quantities will exactly cancel out to give this thing.
Yeah, I understand that. Like, I was worried about just because it's a mixed tensor, right? So
Yeah. So that's why, na. I mean, when there is a covariant, I have I down with a bar on top. When it is, if it is contravariant, when it is covariant, it is K with a bar down.
okay, got it. Yeah, got it.
Okay. Yeah. So this is the covariant tensor. Now, let us do one step further. Now I want to ask so I have covariant derivative of a contravariant vector, which is Aij is equal to Aij plus gamma Ikj Ak. Okay. Now let us do the following. This, how did it come about? I had DAI is equal to DAI plus gamma I kj dk dxj. This is what we had.
Yes.
Okay. Now, now next I want to find out what is BI semicolon J, the covariant derivative of a covariant vector. How will you do it? There's a trick. The trick is a scalar quantity does not change. So that is why in a scalar quantity, covariant derivative and partial derivative are the same, right? So I will construct a scalar quantity phi, which is equal to AI BI. Okay. And I will now calculate. Yeah, just a minute. Yeah. So now let me see what is the coordinate change in phi. Now, delta of phi is equal to 0 because the scalar field, the scalar quantity does not depend on coordinate. So changing the coordinate vectors, the unit vectors does not change phi. So delta phi is 0. So I have delta AI BI is 0, which I can write as delta AI BI is equal to minus AI delta BI.
Yeah.
Okay, fine. Now let me substitute. Now I know what is delta AI. Delta AI is basically gamma I A B A delta XB. Okay, that's how we define, no? Sorry, with a minus sign. So remember, that's how we define gamma here.
Yes. With the minus sign.
With minus sign. Now AI, so I have minus gamma I just a minute. Okay, gamma I. Okay, let us see. Gamma I AB AA BI delta XB is equal to minus AI delta BI. All right. Now let me just make some changes in indices, dummy indices. I'll make it K. I'll make it K. And I will make this A dummy index also K. Is that all right?
Yes.
Now this is again true for any arbitrary AK, whatever be the AK. Now the argument is, suppose you have a matrix into a vector, okay, is equal to another a matrix into the same vector. If this is true for any vector, then A and B have to be the same, right?
Yeah.
Yeah.
It's the same argument here. It is true for any vector AK. So, and minus minus becomes plus. So I have gamma I KB BI delta XB is equal to delta BK. See the difference? That one, when I have the change, the coordinate change in the covariant vector, there is a change in minus sign. And now as before, I will say that the change, the physical change in BK, which is BK, will be equal to dBK minus gamma I KB BI delta XB. So now I'm going to subtract it out. So now since there is no minus sign here, there's a minus sign which comes here. Okay.
Yes.
So I have dbk is equal to del bk by del xb delta xb minus gamma ikb bi delta xb, which means dbk is equal to bk comma b minus gamma ikb bi into delta xb, which basically says that the covariant vector k semicolon b is equal to covariant vector k comma b minus gamma ikb bi. Is it okay?
Yes.
Yes.
Okay. So now we have got these two. Now we can get even more greedy. Okay. I will now say that let me consider a tensor. Let me consider a tensor ij, which is given by ai bj. Right? Ai is a vector, bj is a vector, so it's a tensor. All right.
Yes.
And I want to find out delta of Tij, which will be equal to delta of ai bj plus ai delta of bj. And I will write this as delta of Tij will be equal to so this will be gamma a I A J no. Okay, I've just substituted for delta x, delta AI. I mean, this quantity is same as this. Correct?
Yeah.
Okay. This plus similarly, AI, I will have gamma A PA J delta XB B okay, that's all right. Yeah. Okay. Is it all right? Yes, no?
Yes. I guess.
I've just substituted for this delta, this one like this.
Yeah. Yeah. Yeah.
Okay. And now I will write it as delta Tij is equal to, let us see this. Gamma AIB AABJ plus gamma AJB AIBA into delta XB. All right.
Yes.
Yeah.
And so d of Tij is equal to d of Tij minus gamma AIB. Now AABJ is what? It is TAJ, right? By this definition.
Yes.
Yes.
Minus gamma AJB TIA. So I have got the transformation properties of the tensor. And so, and okay, so this,
Wait, delta XB also.
yeah. So this, sorry, yeah, this times delta XB. And so I have d Tij is equal to del Tij by delta XB minus gamma AIB TAJ minus gamma AJB TIA, this whole thing into delta XB, which means Tij semicolon B is equal to Tij comma B minus gamma AIB TAJ minus gamma AJB TAI. Basically, you need to look at the following. For when you are doing the first term, A, you forget the fact that there is another tensor notation. Treat it as a covariant vector and do it. Then you freeze this, treat this as a covariant vector and do it and add everything.
Yeah.
Now, in this way, you can actually construct any of these covariant vectors. It's basically, suppose I have S, I, J, K, covariant A. This will be S, I, J, K, semicolon A. First, let me do it one by one. First, I have I, which is contravariant. So I'll put a plus sign. And then I'll put a gamma. And this will carry this I here. Then there is derivative A, which will come here. Okay. Derivative A will come here. And then I will have S. A has, this SI has gone here. So I will put a dummy index here and a dummy index here. J, K. That is, J and K are left untouched. Only I is replaced by this as if it is a contravariant vector. Next, gamma. This is, now I want to do it with respect to J. So I will have a J. And then the derivative with respect to A. So I will put an A. I have an S, I. Now J has gone here. So I will replace this as BB, K. All right.
Yeah.
Now the K is a covariant thing. So I'll put a minus sign. I'll put a gamma. Just like covariant, now for this K is down, so the K will appear here. Okay. And now I'll have Sij. Since K has appeared here, I will put a B and a B. And the quantity by which it is being differentiated. So you have got this. Are you with me?
Yes.
Yes.
Sir.
Okay.
And higher orders of, tensor.
Everything you can see, you have all these higher orders. You just say all covariant indices will behave like covariant vectors one by one.
Hmm.
All contravariant indices will behave like contravariant vectors one by one.
Okay.
Okay, for example, if I take this, Okay. If I take this, now suppose I just focus on I. What will happen? J goes away, K goes away. J goes away, K goes away. Okay. J goes away, K goes away. Okay. And these are irrelevant because there are only two indices. This is basically the contravariant vector. Right?
Yeah.
I mean, this is the covariant derivative of a contravariant vector, which I just did for AI.
Yeah.
Okay.
But my
Similarly,
question was semicolon A comma C something like what
semicolon.
like K semicolon A and B, like partial derivative with respect to A and B.
I will come to it. That is where the crux of general relativity will come. You see, I will come to that. That is what, that kind of an object is what will actually see, because in this, for example, suppose you were to take polar coordinates. Even there will be non-zero gammas, right? Although it's a flat spacetime.
Yeah.
Okay. It means gamma cannot by itself tell you about the curvature of spacetime. When you take two derivatives, that is where the curvature of spacetime will first be introduced, which is a measure of curved spacetime, which I will come to. Okay. I mean, that is a complete full lecture on its own.
Okay.
Okay. Now, similarly, if I just go here, I want to treat J, I remove I, K, I remove I, K. Now, I is to be removed, so this term will go away. I is to be removed, so this term will, no, I and K are removed, so this is there, so J is, so okay, so J is retained, so I will have I and K will go away, and then this will go away because that term goes away, since this is also a contravariant vector. Okay. So in terms of the J coordinate, J index also, it is transforming as if it is a contravariant vector. All right.
Yes.
Edil?
Yes.
Oh, this guy has run away, huh? Anil. Okay. Okay. And so, okay. And now, okay. Now I'll take K. So what I will do is, I will remove IJ. I will remove IJ. IJ I will remove, so this will go away. IJ I will remove and this will go away. And then I will remove IJ. And this is the thing for a covariant vector. Covariant derivative of a covariant vector. So what I'm saying is, you just take the tensor, first write the partial derivative, then write each term for each, I mean, the covariant indices one by one, then contravariant indices one by one, and put the appropriate sign. You'll get it.
Yeah.
Yeah. Got it.
So that is the thing. So this is the, so this now, so it means that when you are writing physically relevant important equations, all the partial derivatives will be replaced by covariant derivatives, provided it's a tensor equation. Okay, just to give you an example, I'll just stop with this. Maxwell's equations, I had so if I had Fik, comma I is equal to Jk, right? Okay. This is the Maxwell's equation in flat spacetime, right?
Yeah.
Now, you know that this is a vector.
Mm.
You know that Fik is a tensor.
Yes.
Okay. In flat space-time, this is also a tensor.
Yeah.
So, in flat space-time, I can always write it as semicolon because semicolon and colon and semicolon and comma are the same.
Yeah.
Now, this is a tensor equation
Valid for any space.
because the covariant derivative.
Yeah.
And once it's a tensor equation, it is tensor equation for whatever coordinate transformation. So, it is true in general for even in curved space-time.
Yeah.
So, the Maxwell's equations are replaced by instead of comma, semicolon. And this is true for anything. So if suppose I have a quantity, suppose a quantity equal to another quantity in flat space-time, I write it in the form of a tensor. Once it's a tensor, it is true for tensor for any coordinate system. Is that okay?
Yeah.
Yes.
Okay. Yeah, I think I'll stop with this. Yeah.
Yes, yes. Good night.
Okay.
Good night.
Good night. Good night. Yeah.
Thank you.
Thanks.
Bye.
Bye.